a demo of how we could actually implement an example of an IRQ and the corresponding driver and so on Renode, right. Debugging interrupts is, if anything, even harder than debugging regular code, because in general interrupts are being generated by some external device. It is not a pure software thing that you are dealing with anymore, right. But there are a few things that can be useful for us, right. In our case, one of the things is, after all, we are working with a varilated model, right, which means that we could potentially dump out a varilated VCD, an entire trace file which tells us that this is how the system is behaving, and we can go in there and look at whether the IRQ out signal is actually becoming high at any given point in time, right. It is not very straightforward, because remember that you are trying to deal with the interaction between a CPU which is running at an effective internal clock of possibly hundreds of megahertz, versus you are also sort of co-simulating it with a piece of hardware which is still being emulated at a clock speed of possibly at least hundreds of kilohertz, if not hundreds of megahertz, right. Now ideally what that means is that you iron out as many bugs as possible in your RTL without going into co-simulation, right. You want to have as much of your RTL verified as possible before you get into co-simulation, but at some point you still need to figure out the bugs that happen due to the co-simulation aspects also. So checking the hardware is one of the most basic things that you need to do. The next would be something, check the wiring itself, because after all in Renode we need to make sure that our REPL platform, right, is correctly specified and the value at which we are trying to connect to the GIC is specified correctly. We need to make sure that our device tree has been properly specified and matches with what is there in Renode, or appropriately what is there in our actual hardware. The interrupts are wired properly, and that these two, what is there in Renode and what is there in the device tree, actually match with each other, right. And we also saw that there is this /proc/interrupts, which is a very useful piece of information, because it actually tells us what interrupts are present in the system and active. We can also make sure that the driver itself has been loaded by looking at the dmessage command. In our case, of course, all the messages are being printed out directly onto the console, right. So all of these are potentially useful things to debug, primarily in the scenario where you find that somehow the IRQ isn't counting, right. It is not progressing as you expect, right. And it's always a good idea to sort of have some relatively easy to debug mechanism in place, right. Even if you are trying to set up a system which has some fairly complicated IRQs, have a simpler model, something which you can trigger it into some kind of a debug mode where it will artificially generate a IRQ for you to respond to, just to verify whether at least the driver is responding as expected, right. So having those kind of functionalities is always useful from the point of view of how do you debug a hardware plus software combination. Now just continuing on the same topic, right, you might also find that sometimes the IRQ just fires once and never stops, and then stops, it never counts again. That's interesting. The most common reason for something like that would be that you are not clearing the interrupt as required, right, and you need to make sure that basically you have some appropriate part in your interrupt handler that is actually doing the W1C in order to clear the status bit. And you might also have a scenario where the kernel basically starts giving some other kinds of error messages which are unknown, which have nothing to do with either your RTL code or your driver code. It might be that somehow the handler is sort of returning something which says IRQ none, in other words nobody is responding to this, right. It could be that if you have not actually checked the status bit and cleared it, right, you might just be sort of returning IRQ none without clearing it, which means that it's repeatedly getting hit by the same interrupt again and again and again, right. So the point of this was not that this is some kind of an exhaustive list. These are common bugs that occur when you are trying to implement interrupt handlers, and the only real way of getting good at this is unfortunately by practice, right. But it's good to know some common techniques and try those out, and then sort of implement more of those and see how you can figure out how to get interrupts interrupt based systems working. So a couple of closing words regarding interrupts, at least before we go into the software implementation side of things, right. Interrupts typically tend to have quite a bit of overhead, and we can sort of quantify that, right. The context save that happens when I actually get hit by an interrupt typically takes somewhere in the region of a 50 to 100 clock cycles. Acknowledging the GIC just to sort of let it know that the interrupt has been received, not sort of clearing the interrupt yet, but just acknowledging to the GIC itself takes around 10 to 20 clock cycles. Executing the handler in our case was relatively small. What we did was we just had atomic increment of an IRQ count, but we also had some kind of a message being printed out which actually read the IRQ count and was creating a string. Now that could anything which involves something printing is usually, as we will see later, not a good idea to have inside an interrupt handler, right. You have it only for debugging purposes. In general, especially if you are expecting a relatively high rate of interrupts, you do not want something which actually prints something inside an interrupt handler, because that could change your handler execution time from hundreds of clock cycles to potentially thousands of clock cycles, right. So you want to keep that as short as possible. The end of interrupt signaling going back to the GIC also takes 10 to 20 clock cycles, after which the CPU then needs to come back to whatever it was doing before. Remember that it was interrupted, it saved context, went away, did something, but it comes back and needs to proceed with what it is doing. In other words, it needs to restore that context and resume. So total would be anywhere several hundred clock cycles at least for an interrupt handling. And if we are sort of looking at that we have some kind of a 1 Hertz wrap rate, that is 1 interrupt per second, then suddenly this is not much of a problem, because with a 50 megahertz clock I am only talking about an extremely small overhead, right, 400 clock cycles out of 50 million. But imagine that instead of a 1 Hertz wrap rate, I had a 1 kilohertz wrap rate, right, 1000 times per second. This suddenly jumps to nearly a 1% overhead just to respond to interrupts. And if I made this a 1 megahertz wrap rate, then I can potentially get to the point where I am actually spending more time handling interrupts, right. I do not really have time to handle interrupts, because at 1 megahertz interrupt rate, I do not have 200 to 400 clock cycles between interrupts. I have only 50 clock cycles between interrupts, right. I can't even like process all of them anymore, right. So as we said earlier, right, if you have a relatively low rate at which the interrupts are happening, then it makes sense to use interrupts. In this case, for this kind of number and for this kind of overhead associated with the number of clock cycles, perhaps 1 kilohertz makes sense. As we saw, that would be less than a 1% overhead associated with the system, right. But for something significantly more, let's say that your clock frequency was less, or that the overhead associated with handling an interrupt was more, then even 1 kilohertz might be a problem, right. So all of these numbers are relative. Do not take any of these as some kind of hard and fast rules. You have to be able to calculate it in the context of whatever it is that the system that you are trying to build, right. So for example, if you have a processor running at, let's say, 100 kilohertz and your interrupt handling takes 1000 clock cycles, and you want not more than 1% overhead associated with interrupt handling, then you can automatically do some computations to find out what's the maximum rate at which you can process interrupts, or rather at what point do you say that interrupts are a bad idea and I should probably just poll or do something else in order to make sure that I am able to process the data without losing any information. So essentially, when you have very fast operations, of course I have once again put in a number like 1 microsecond over here, but as I said, this depends on the system frequency, the interrupt frequency. But if it is fast, in other words, there are many of these events happening relative to how fast your processor runs, polling might actually be faster, right. So whenever the main reason for using polling is that it's a one-time initialization of the driver, you do not need to keep jumping into a driver handler each time, But what it means is that you are stuck in this tight loop, not really doing anything else, just sort of you keep waiting for something, you do something else, and then you need to come back and basically look for the next event again. On the other hand, when you have an unknown amount of completion time, you do not know how long the peripheral is going to take to execute, or you really want the CPU to be free to do other work during that time, or you want to handle multiple event sources, right? For anything other than a completely embedded system with a single functionality, you typically have multiple different kinds of event sources and functions that you need to handle, right? You are pretty much going to be forced to use interrupts at that point. So just to summarize everything that we have discussed over here, right? Why do we bother with interrupts? Primarily CPU efficiency, most likely power savings, and responsiveness. As I said, you can have something where you can have interrupts corresponding to keyboard or mouse events and have them immediately wake up and get your CPU or get your system to do something, right, without necessarily having to sit over there and wait for the keys to be pressed all the time, right. So on the other hand, as soon as a key is pressed, it immediately activates the system and goes in there and starts responding to whatever it was that you wanted. There are different ways in which interrupts are typically wired at the hardware level. Level triggered persistent interrupts are the most common for peripherals that are in our control, that we are trying to create. Transient external systems are typically going to be edge triggered, but are harder to control and harder to implement or design for, right. The GIC is a generic interrupt controller. It is specific to ARM, but most other processors have some other similar kind of a setup, right. So Intel processors or the x86 processors have something different, which also allows you to sort of consolidate interrupts from many different sources and pass them on to the CPU. RISC-V, for example, has typically tended to try and use a similar approach to ARM just for compatibility and the fact that there are many existing IPs that are compatible with the bus structures used by ARM, and therefore RISC-V also tries to be compatible in a lot of different ways. The important thing about the GIC architecture is it basically has a distributor which routes the interrupts, right, or rather collects interrupts from many different places and then routes them to the appropriate CPU. The CPU interface actually delivers the interrupt to individual CPU cores, and SPI, not to be confused with the serial peripheral interface, in this case it's the shared peripheral interrupt, is used by us for connecting peripherals. In order to get all of this integrated with the Linux OS, we need to provide that information in the device tree. We use a 3-cell format which basically describes the wiring using the interrupts property, right. So we have the three things, which basically the first one says that it's an SPI or a PPI, the type of interrupt. The second is the actual number, which is something that we choose, but we need to choose it appropriately so that depending on how the GIC is set up and how we are able to connect things to it physically. And the third is usually used to indicate that this is a level triggered active high interrupt, or if it is something else, then there is an appropriate code that can be used over there. So all of these are useful from the point of view of how we wire up the hardware and how we get the basic structure of interrupts in place, right. And as you can imagine, actually writing the software handlers for interrupts is non-trivial. It requires some fairly careful handling over here, and we will be looking at that in a little bit more detail in a further set of lectures.